thank the organizers of the conference for giving opportunity to make a talk here. Let's consider a surface of constant curvature, -1 or 1, so it is a hyperbolic plane or a sphere, and consider the group of isometries of this surface that preserve the orientation. So in the case of a hyperbolic plane we have a group PSL2, and in the case of sphere we have SO3 group. One can consider this group of isometries as a bundle of unit tangent vectors on our surface, and this bundle is a weak symmetric homogeneous space. Here our group acts natural way, and the second multiplier SO2 acts on the tangent vectors by rotations by the same angle. And the stabilizer SO2 is embedded in this direct product in the antidiagonal way. And we consider left invariant Riemannian matrix on such homogeneous spaces. And by the Riemannian problem, I mean the following questions. First of all, it's investigation of geodesics optimality. We need to, for any geodesic, we need to find a cut point. It's a point after which the geodesic is not the shortest arc, and due to the left invariance of the problem, it is enough to consider geodesics that starts at the identity point of our group. So I call the cut locus the set of the cut points of all geodesics starting at the identity point. And another question is to determine some geometric characteristics of this homogeneous space, in particular the injectivity radius and the diameter. Diameter in the case of SO3, because in the case of PSO2 it's infinite. So this problem can be formulated as a control problem, and let me introduce some notations. Let E1, E2 and E3 be a frame in the V algebra in which the killing form and the metric have diagonal form. The killing form has eigenvectors 1, 1 and plus or minus 1. It depends on our group. If it is a group of isometries of a hyperbolic plane, there is minus 1. And in the case of isometries of a sphere, there is a plus 1. And in the same frame, our our metric have eigenvalues I1, I2 and I3. And our case is I1 equals to I2 due to the invariance under the SO2 action. And let eta be a parameter that measures the ablatiness of small spheres of our metric. So we have a series of Riemannian problems. When eta is less than -1, we have a Riemannian problem on PSL2 group. When eta is more than -1, we have a Riemannian problem on SO3 group. And when eta tends to -1, it is equivalent to I3 tends to infinity. It means that it is very hard for us to move in the third direction. So it's in the limit we have the Riemannian problem on PSL2 group or on SL3 group. I'd like to say about previous known results. The Riemannian problems on SO3, SL2, and the group of isometries of Lobachevsky plane solved by Valery Berestorsky and Irina Zubareva, and also there is work of Ugo Buscain and Francesca Rossi. And in the case of SU2, the Riemannian cut locus is known for I1 that is more than I3. There is some connection to our problem because SU2 is the two least covering of SU3. And now I would like to present the new results of the cut plots. And here you can see the pictures, and I will explain what it is. It is the plots of the cut locus in the two leaves coverings of our groups in SU11 and SU2. This covers SU2 and this covers SU3. So the PSL2 group is homeomorphic to the solid torus, and in this picture this torus is the area between two cups of a hyperboloid. Really, this is a three-dimensional picture, but due to the invariance under rotations, we can consider the section of this picture by the vertical plane. So this area between two cups of hyperboloid, and we need to identify the points of these two cups. This is the solid torus, and the cut locus is the plane, the red cup there. In the case when eta is less than -3/2, and if eta is more than -3/2, an additional component of the cut locus appears. It is an interval. You can see there are two intervals, but it is one interval because we need to identify the points, and the same and the similar situation are in the case of SO3 group. When eta is more than -1/2, we have a projective plane as a cut locus. The SO3 group topologically is the three-dimensional projective space. We draw it here as a ball, and we need to identify antipodal points of the border of this ball, and when eta...
Sorry, could you recall, what is eta?
Eta, it is the parameter which measures the lateness of small spheres. It's the fraction of aging values, -1, and plus or minus before the fraction, it depends on the case of the plus is for a sphere and the minus is for...
You uniformly, for both groups you do it in the one.
Yes, the description is the same for both groups. So when eta is less than -1/2, an additional component of the cut locus appears. It is an interval, and there is geometric interpretation of this strata, the global strata, a plane in the case of PSL2 and a projected plane in the case of SO3. It is the set of all central symmetries of our surface. And the local strata, the local stratum is an interval of some rotation around a fixed point on our surface. And this local component appears only when there is no triangle which sides are equal to the eigenvalues of our metric. And when such triangle exists, then I know the mechanical interpretation of the Riemannian problem on SO3. It is the free motion of a rigid body fixed in one point. So it is the right case. And there are other cases. I don't know any physical or mechanical interpretation in the cases. Here you can see the equidistant wavefront in these groups in most complicated cases when the cut locus have two components. And there is a connection with the Riemannian problem. When eta tends to -1, the Riemannian problem converges to Riemannian one. It means that the parameterization of geodesics, the cut loss is the cut time converges to the same objects in the Riemannian problem. And in the Riemannian problem, the global component of the cut locus has the same interpretation. It's the central symmetries, and the local component in the case of Riemannian problem is a circle of all rotations around a fixed point. Here presented results about the cut time. The theorem states that if there is a triangle of the sides equals to the eigenvalues, then the cut time is the first positive root of such equation. It is 2-degree polynomial of trigonometric or hyperbolic functions. And when there is no triangle of the sides equals to eigenvectors of the metric, then there are two cases. there is a cone in the co-algebra, and if the initial momentum of geodesics lies inside the cone, the cut time is the simple fraction. And if the initial momentum is outside the cone, the cut time is the first positive root of that equation. And in the case of PSL2, we have a family of geodesics that are optimal anywhere.
Okay, sorry, what is P in brackets?
P.
Сколько, что такое?
It is the P in brackets. It is the initial momentum of geodesic. It is an element of the algebra. The cut time depends on the initial momentum. I have some other results on the injectivity radius and the diameter, but there are 4 different cases dependent on parameter eta, and I don't know yet the meaning of the critical values of parameters. So I don't present this complicated formulas here. And the similar results I have for SL2 and SU2. And I'd like to say a few words about the method. First of all, we need to find the parameterization of geodesics via Pantelian maximum principle. Here you can see the Hamiltonian of Pantelian maximum principle and the Hamiltonian system. And the next line is the exponential map. It maps the level surface of the Hamiltonian that corresponds to the geodesics with natural parameterization. And this level surface turns to the timeline, and the exponential map is just moving during the time t along the Hamiltonian vector field, with starting with the initial impulse p and identity point of our group. And in our case, the parameterization of geodesics is just the product of 2 one-dimensional subgroups. So it's simple enough. In the case of SO3, these exponents give us trigonometric functions, and in the case of PSL2, the first exponent gives us trigonometric or hyperbolic functions, and the second gives us trigonometric functions. So the formulas of parameterization is 2-degree polynomials of hyperbolic or trigonometric functions. Next, we study symmetries of the exponential map. Means the symmetries of the vertical part of the Hamiltonian system that produce the symmetries of geodesics. Then we find the first Maxwell's data that corresponds to symmetries, and then we verify that the conjugate time is more or equal to the first Maxwell time for symmetries. In general, there can be some Maxwell points that are not corresponding to our symmetries, but if we are lucky enough, we can prove that the exponential map is a diffeomorphism of a domain that is bounded by the first Maxwell time for symmetries to the complement of the Maxwell's data in our group. And if we have such diffeomorphism, that then the first Maxwell's data that we found is exactly the cut locus, the closure of the Maxwell's data is the cut locus. Here, the end points of these vertical intervals are the conjugate points. Thank you for attention.
Questions? I would like to, did you check the inactivity domain? So when you consider exponential map, Riemannian exponential map, I would say, for your metric, so you have a domain in the tangent space of the source where before cut locus, I would say.
Yes.
Did you check if it is convex always or not, or in some cases it is not convex, because for certain application this is an important property. I believe that you can describe this domain more or less explicitly after your results.
I don't know. It seems that it is possible and quite simple, but
because it's important for some application, particularly optimal mass transportation we discussed. It's a very important property.
it seems to be simple, but right now
You didn't check.
Unless it is star-like.
It's star-like, it's always star-like. But if you are around sphere, it is a convex. But then when this difference between maybe not. It's very because there are some properties which are responsible for smoothness of mass transportation